Hello everyone, my name is Elham Mirzaei. I came from HTW, University of Applied Sciences, Energy and Information from Berlin. Today I am here to give my speech about safety cases for adaptive systems of systems, state-of-the-art and current challenges. In the upcoming slides, I will start with a brief introduction, following with the captured challenges for adaptive SOS, and giving a report regarding safety approaches and safety cases methods, and finally describing the initial dynamic approaches. Let's start with a brief definition of system of systems, or SOS, which is a complex, purposeful set of systems with characteristics such as autonomy, in terms of the ability to make independent choices, belonging, in terms of systems choosing to belong to a specific SOS on a cost-benefit basis, connectivity, in terms of interconnections among the systems, and diversity, or in other words, heterogeneous systems, as well as emergence, in terms of supporting early detection and elimination of bad behavior. Based on this definition about SOS, we can now define adaptive SOS, which are a type of SOS, first of all, that are manufactured to achieve a predefined mission while they involve a large number of interacting entities with persistent reconfigurations, and they are trying to changing based on changes that is happening in their context. They ordered through self-organization, and obviously they are evolving during their life cycle, and their complexity is increased. There are two examples of such adaptive SOS that I can mention here. One is the vehicle platoons, or virtually coupled trains in transportation, and the other could be collaborative machines and transport robots in a factory of the future. Many of these applications of adaptive SOS mostly are safety critical systems, and ensuring safety for adaptive SOS is really challenging because either all relevant configurations must be assessed at design time, which is not feasible solution, or assessment must be done dynamically at runtime. And this is what is motivating us in order to step into this safety research topic. Following the introduction, here I would like to make an example of SOS in order to clarify the characteristics of such a system. As you can see, our example here is the factory of the future, in which a fleet of transport robots are collaborating with machines in order to fulfill the requested transports that are coming from those machines, and the robots must be able to fulfill these jobs autonomously. Meanwhile, these transport robots are trying to react also onto the changes that are happening in their environment by adapting their configurations, which also includes their interactions as well. And at the end, this collaboration among these members, which could be machines, this machine execution system, or all the robots, is happening in order to fulfill the shared objectives at the level of the factory, which is the highest level and which is the SOS level. So in general, there are three levels of flexibility we can define for selecting new reconfiguration for such a system. The first category is predefined selection. This type of selection is supported by design time safety concepts. The second type is constraint selection. This type required partially runtime safety concepts as well as the design time safety concepts. But for the third type, which is the unconstrained selection and is the most challenging type of the configuration, the design time safety concepts are not anymore sufficient. Therefore, the runtime safety concepts is required as well on top of that. In the previous slide, I already talked about normal situation in the factory of the future as an example of adaptive SOS. Now, here in this slide, I would like to talk about failure situation. Considering again the same example, robots collaborating within the factory SOS, but one robot, here robot number 4, experiences sensor failure and is blocking the hallway because it cannot move anymore because it doesn't have the correct sensor information. The risk here is that, the safety risk here is that the robot with failed sensor cannot move safely. Therefore, there is a risk of hitting obstacles or, more importantly, hitting human operators who are sharing space with these transport robots in the factory. Therefore, a reconfiguration is required at the level of SOS. Here the reconfiguration would be that robots trying to collaborating with each other and agreeing on one optimal strategy to fulfill partially the contradicting goals. Here the goal is that maintaining the safety and evacuating the hallway once again. And therefore, one robot is sharing the sensor data with the failed robot and trying to escort that failed robot out of the hallway safely. By this example and this failure scenario, I tried to highlight the necessity of runtime safety assurance that is required for adaptive SOS to assess safety of candidate SOS configurations at runtime. There are many captured challenges for adaptive SOS in order to ensure true-life safety for such a system. Here I try to highlight the most important ones. First is complexity of adaptive SOS, which is challenging in terms of development of such a system and as well as safety concepts. Second is the openness of adaptive SOS in terms of collective behavior of SOS, which is not known at design time. The third challenge is dynamic nature of the relations among members of SOS. And the last challenge is that it is really difficult to foresee and assess all the relevant configurations, which could be hundreds or thousands, depends on the complexity of the system at design time. Therefore, here we can have different possible solutions. First is either we restrict the configuration selections, which is not an optimal solution because we are literally, by choosing this solution, reducing the flexibility of such a system. And the second is restricting the assurance effort by adding runtime safety assurance. And here, where we would like to furthermore go and talk about the challenges, the methods, and the outlook we will have to cope with these challenges. After capturing all those challenges regarding adaptive SOS, now we would like to try to find the possible solutions that are available in the research currently as an approach. There are different safety approaches that we can find, but here I would like to highlight those approaches that we think could be helpful to cope with the listed challenges. Safety case is a traditional safety approach, and it is defined by UK Defence Standard 0056 as a structured argument supported by a body of evidence that provides a compelling, comprehensible, and valid case that a system is safe for a given application in a given environment. Based on this definition, there are 4 key elements for this approach: claims that are defining properties of the system, evidences that are used as the basis of the safety arguments and could be a fact, assumptions, or subclaims. Arguments that are linking the evidences to the claims, and the context, which is the environment in which all those analyses and arguments are valid. Traditionally, the safety case approach is constructed at design time and for the entire system or SOS. As I already declared, the traditional safety case is done for the entire system or SOS. This imposes a problem of redoing the entire safety case upon any changes that happen in the SOS, and this leads to a considerable effort and high extra costs. Therefore, another approach was introduced in order to cope with this challenge and reduce this problem, which is called modular safety case or MSC. Modular safety case actually is combining elements in such a way that they can safely be composed, removed, and replaced while enabling independent reasoning concerning the safety concepts. The benefit of this approach, as I already mentioned, is that it is reducing the system complexity by breaking down the system into modules and submodules. And as a matter of that, it is increasing the interchangeability of the system components. As you can see in the picture, if one specific module in a system is changing, instead of changing the whole safety case of the system, we just change the safety case related to that specific modules. Here you can see module number 1 is replaced by module number 4, and we just replace safety case number 4 instead of redoing the whole safety case for the whole system. And the last benefit it is that as a matter of reducing the effort, it is obviously also reducing the cost of recertification of the changed systems. Now the question is that how we can modularize systems into submodules and modules. There are two approaches to do so. Approach A is suggesting to following the system hardware-software architecture hierarchy. It could be component-based. As an example, on the right side, you can see part of the functionality of transport robot, which is the navigation system. And this navigation system functionality has two sub-functions, which is the obstacle perception and the position perceptions. And each of these functions needed some inputs from specific hardware, which are the sensors here, LiDAR, 2D camera for the obstacle perception, and IMU, GPS, and odometry for the position perceptions. And normally for each of these module, according to the modular safety case, we should define a safety case, as you can see. But there is another approach, which is approach B, that it is suggesting to do some optimization after modularizing the system based on the hardware-software architecture hierarchy. For example, here in this example, considering that the position perception function, it is not expected to be changed in the future, and it is developed by one manufacturer, including all those hardwares. Then we don't need to define for each of them one safety case. Instead, we do the optimization by merging all those safety cases relating to this specific function and reducing the number of safety cases. And this is how we go for approach B and optimize our modularization. In summary, modular safety case can be used in the scope of adaptive SOS when the flexibility of reconfiguration is limited only to predefined of constraint selection, which is totally done at design time. However, this method is not sufficient for constraint and unconstrained reconfiguration selection at runtime, which were defined at the beginning slides. Among the available safety case methods, dynamic safety case DSC is one good solution proposed by Ivan Denny et al. In order to cope with challenge of mismatching that can happen between design risk analysis and the operational requirements. These assurance techniques exploit the runtime related data to continuously assess evidences and evolve the safety arguments, verifying whether the claims are still valid or not. There are three fundamental principles for this method. The first principle is proactively compute the confidence and update the reasoning about the safety of ongoing operations. The second principle is that providing an increased level of formality in the safety infrastructure in order to enable automated support for the safety reasoning. The third is providing a mixed automation framework to generalize from the notation of complete standalone argument to a partially developed but well-formed argument with open tasks assigned to various stakeholders. The benefit of this method is that it is actually extending the safety management system concepts by providing continuous true-life safety updates based on the relevant physical systems and runtime events. And second, filling the gaps between the documented safety reasoning and the actual safety of the system. In summary, to ensure the true life safety for adaptive SOS, the safety case assumptions often must be reanalyzed at runtime, and this is perfectly can be done by dynamic safety case. Therefore, dynamic safety case is used in the scope of adaptive SOS when the flexibility of reconfiguration predefined of constraint selection at design time and as well as constraint reconfiguration selection at runtime. In the previous slides, we reported the safety case methods that can be taken as a solution to cope with the challenges of adaptive SOS. The first method was modular safety case, which is reducing the system complexity by breaking down the safety arguments into modules, and as a matter of that, reducing the cost and impact of change during the life cycle of the system. The second approach was dynamic safety case, which is bridging the gap between taken assumptions at design time and properties of the realized system during runtime, and as well as coping with the openness of SOS and dynamic nature of relation among its members. However, additional measures required to analyze and maintain safety for adaptive SOS. Therefore, we propose to merge these two methods into one method called Dynamic Modular Safety Case, DMSC, in order to cope with the challenge of unconstrained selection during reconfiguration at runtime, which was the third type of reconfiguration and the most challenging one, and also benefiting from both methods' assets. One of the good initial dynamic approaches in this direction is modular conditional safety certificates or concerts, which is proposed by Daniel Schneider. This approach based on a series of formalized guarantee demand relationships that can be composed and evaluated at runtime. In this method, modular conditional safety certificates with some certain degree of variability is predefined at design time, but can be supported by runtime evidences as an additional operand of the conditions. Obviously, this method is very well mapping with dynamic reconfiguration based on constraint selection. But since this method is a post-certification artifact that should be initially created during design time, cannot be supported by unconstrained selection, not yet. However, this team introduced a conceptual framework named B-Space, which is operationalized by Concert, which can be taken as a first steps toward developing safety guarantees for unconstrained selection in the reconfiguration. For stepping towards dynamic modular safety case, there are some open challenges that we must take a look at. The first challenge is dynamic monitoring. For instance, we should be able to answer questions such as which module's properties are precisely in exposure of changes during operations. The second challenge is runtime analysis, which imposes some set of steps that needed to be done at runtime, such as identifying the changes, propagating the changes through the respective affected modules, measuring the impact of changes, reviewing and assessing the arguments, and finally being able to embed the relevant evidences into all these analyses. The third challenge is evaluation and decision making at runtime. This is where the system must be able to take action with the ability to construct and analyze new modular safety case at runtime. This challenge specifically imposes two sub-challenges, including machine readability and symbolic processing, as well as automatic regenerating or updating of modular safety case, which can be done either fully or partially with human review. So, the challenges that are listed here remains to be solved for Open Adaptive SOS. And we would like to contribute on mastering these challenges, specifically the evaluation and decision making at runtime in the future work. Thank you very much for your attention. I would happily answer questions may arise.